Actually, a nice chapter, a nice reading for clustering is actually the chapter 14.3 of Hasti, Tibshirani, and Friedman. Actually, this is available online, which is nice. And also, if you want to read more, you can also, about more foundational, you can read a chapter that I wrote recently with Pranjal Awasthi. Okay, cool. So let's get started. Okay, so what is clustering? So, well, I'm sure you guys know many applications of clustering. So, right, first of all, even before talking about applications, what it is informally. So, informally is the goal when doing clustering is to somehow automatically partition unlabeled data into groups of similar data points. So, we only have unlabeled examples, and we want to somehow automatically partition so that similar points get into similar parts. Okay, and why would you want to do that? Well, there are multiple reasons. For example, you might want to automatically organize large amounts of data, or you might want to just understand hidden structure in data. This is a bit more like unsupervised learning, the second goal. Or you might just want to do clustering as a pre-processing step for further analysis of the data, right? We might, for example, you might want to, for an example would be for visualization purposes. So people, if you want to visualize data, you might want to do clustering because it might be easier to visualize that. Okay. Now, in terms of applications, I mean, there are many, many applications. It really, I mean, clustering really comes up in all fields. So, for example, just to mention a few, you might want to cluster news articles or web pages or search results by topic, or you might want to cluster protein sequences by function, or genes according to their expression profile, okay, or might want to cluster users in a social network according to their interests, right? And this is, actually, this is a popular topic these days called community detection, okay? Or you might want to maybe cluster customers according to their purchase history, right, to do better decision later on, okay, like better pricing and so on. Or you might want to cluster galaxies or nearby stars, for example, by using data in the Sloan Digital Sky Survey. Okay, so many, many applications. I mean, these are just examples of applications, but really clustering comes up everywhere in all fields. And so it's important to understand what type of algorithms do we have for clustering. Okay, and as I already mentioned, so actually Tom already talked about clustering on March 4th, so, but he talked about a very, very specific way of doing clustering by EM algorithm, which is a nice algorithm in general, but doesn't have provable guarantees. And moreover, the derivation that he talked about was very specific to a mixture of Gaussians, okay, a probabilistic model. And so today we'll talk a bit more algorithmically about clustering, and we'll talk both about kind of objective-based clustering, so, or clustering algorithms where we output a partition of the data, and we'll also talk about hierarchical clustering. Okay, cool. So let me start with objective-based clustering. So I'm going to start with a little bit of a general overview of what objective-based clustering is, and then I'm going to focus on the k-means algorithm, or the k-means objective, which is probably the most popular objective used in machine learning and also machine learning. Okay, but what is the problem more generally? So we have a set S of endpoints, and we also have a distance or dissimilarity matrix, a dissimilarity measure specifying the distance between pairs of points. Okay, and this could be something, for example, given by the domain, like if we want to cluster protein sequences, we might have added distance, so the domain experts think it's a good function of distance. Or it can be the number of keywords in common if you want to do maybe, say, news article clustering. Or it can be something based on the Euler coefficient if you want to do image clustering, right? So it can be something given by domain experts, but it can also just be the natural notion of distance if the points are embedded in RD, right? So for example, if the points are points in Euclidean space, we can just define the distance between points to just be the distance in the Euclidean space. Okay, and so the goal traditionally when we do objective-based clustering is to output a partition of the data. And now there are many types of objectives that people have considered. And let me mention one. The most popular one is a k-means objective. Okay, and here I'm writing the definition a bit more generally. So I'm going to specialize in a second for the Euclidean case, which is the most popular one used in machine learning. But the definition can be written more generally. And so here, more generally, we just have as input a set S of endpoints and the distance function, satisfying, say, triangle inequality. And then the goal is to output centers, C1, C2, Ck, which might not be the data points themselves. So I want to output centers and a partition of the points into clusters in a way to minimize the sum over all points of their square distance to the nearest center. Okay, this is what we want to do in the k-means objective. Right? We want to just output a partition, like this one here, and for each part we want to output a center. Each point is assigned to its nearest center, and then we want to minimize the sum of the square distances from sum of all points of the square distances to their corresponding center. Yeah, so that's the k-means, and here's the sum of the square distances. This is while using machine learning. Another objective, let me mention a couple more objectives. So another one is a so-called k-median, where it's the same as k-means, except now we want to minimize the sum of the distances of the points to their corresponding centers. Yeah, so it's just linear as opposed to quadratic here, the penalty. Okay, this is more widely used in like OR, operations research, and theoretical computer science, maybe in the context of, say, passivity location. This is more commonly used. This is more commonly used in machine learning. And there are other objectives, like the k-center objective, where the goal is to find the partition of the data, and we want to minimize the maximum radii. Okay, and there are many others, like mean sum clustering. The goal is to find the partition in order to minimize the sum of the intra-cluster distances, inside cluster distances, and so on. Okay, but these are the most popular ones. And in particular, in machine learning, the most popular one is the so-called k-means objective, right? This objective over here. Okay, and let me just specialize to what people like most in machine learning, namely the k-means, namely the Euclidean k-means problem. Okay, so in the Euclidean k-means case, we assume that the data points are points in RD, in the Euclidean d-dimensional space. And so that's the input. So we have an input, a set of points that now live in the Euclidean d-dimensional space. And we also have as input a number of target clusters. We are looking for k. For now, let's assume that we are given k. We can discuss later where is k coming from. Okay, so we have also as input the number of target clusters. And then the goal is exactly as I mentioned earlier, is to output k centers, C1, C2, Ck. They can belong to, they can be any points in RD, not necessarily the input points. Okay, and then what we want to do is just basically to assign each point to this closest center out of those k centers, and then we want to find the centers, the set of centers with the property that if we sum over all points, the sum of the distances to their square distances to their corresponding centers is minimized. Right, so that's the k-means objective. Is clear to everyone? I'm sure everyone, have you all seen k-means objective? Yes? It's probably yes, because it's very popular. It's widely used. Okay, so that's the k-means objective. And so, right, if you think about it actually, right, so what we do here, we assign each point, right? In this formula what I'm writing here is basically given a set of centers C1, C2, Ck, we assign each point to its nearest center, very, very natural, right? And then if we do so, basically, so given a set of centers, maybe, okay, maybe a center would be, let me just put some centers over here. Right, so if we do so, if we assign each point to its closest center, right, so then we have, so maybe this is a center. Oops. Right, so maybe let's assume that these are my centers, like centers C1, center C2, and center C3, for example, right? If I have here 3 clusters, right? And once I do this assignment of each point to its closest center, then what I get is this type of Voronoi partition, right? So then I'm going to partition the space in this way, like exactly like each point is assigned to its closest center, right? And this is called the Voronoi partition. Okay, and you can, if you think about it, you can easily verify that each of the parts is convex. Okay? So, right, once we do this natural assignment or assign each point to the closest center, we kind of partition the space into convex cells, and this is called the Voronoi partition. Okay, so that's the k-means clustering objective. Now, you might wonder, can we, I mean, this is what we want to do, right? We have as input and data points. They live in RD. We want to find a set of centers to minimize this k-means clustering costs for those set of centers. Okay, now, what do you guys think? Can we solve this problem? I mean, ideally, we would want to solve this problem optimally, right, once we define it, right? That would be ideal, in polynomial time, right? And what do you guys think? Do you think we can solve this problem in polynomial time? I mean, polynomial in n, the number of data points, d, the dimension, and k, the number of target clusters. The number of clusters we are looking for. Do you think we can actually solve this problem in polynomial time? I mean, this objective has been considered for many, many years, actually, in machine learning and signal processing, because actually clustering problems appear also in signal processing. For example, you can use clustering to do image compression or image segmentation. So it appears everywhere, really, not beyond, like, it appears in social sciences, right, and everywhere, really. So people have been thinking about k-means objective for many, many years. Okay, and it's an objective function, you can write it down, and then the natural question is, let's assume that we are thinking about the Euclidean case. Actually, ideally, if I could optimize this in polynomial time, then I would want an algorithm that optimizes it, gives it the optimal solution. Why settle for something like EM that is just a local optimum, right? Ideally, you get a global optimum. I mean, yeah, it could only be better. And so, do you think we can actually solve this in polynomial time? Well, I think the answer is a little bit surprising. So even if you are experts in, say, computer science and in computational complexity, the answer is still a little bit surprising, I think, actually. So first of all, why is it surprising? I think it was known for a long time that if we drop the Euclidean case, if we go back to the definition that I had on the previous slide, if I'm only thinking about this more general case where I have an arbitrary distance function, then it was known for a long time that it's NP hard. So unless P equals NP, which is widely believed not to be true, it was known for a long time that this problem wouldn't be solved in polynomial time. But how about the Euclidean case, right? Because this is arguably the most common one. What if points live in RD? And the answer, I think, it's a bit surprising. So the answer, it turns out that no. The answer is actually, in interesting cases, the answer is no. Okay, so it turns out that it's NP hard to solve it. So in other words, assuming that P is not equal to NP, we cannot find in polynomial time the optimal solution for this objective. And this is true even in very simple cases. When k equals 2, I'm only looking for 2 clusters. Or when d equals 2, I'm only in 2 dimensions. Okay? And actually, so this is a very hard computational problem. It's NP hard. And actually, what's surprising to me is not only that it's hard in these cases, but what's a bit surprising to me is that these results are only proven in 2008 and 2009. Given how long people have studied these problems, it's super surprising to me that only in 2008 they shown that it's NP hard when k equals 2. Okay, this was shown by Sanjay Dasgupta. Okay, and intuitively, I mean, there is a formal reduction, you can read his paper, but intuitively the case on k equals 2 is hard in this case, is because the centers could be any point in the instance space. Okay, so we have many possible choices. Okay, so it's NP hard even when k equals 2, and also it's NP hard even when d equals 2. Okay, for k equals 2 to show hardness, we need a large number of clusters like log n. For k equals 2, for k equals 2, we need a large number of dimensions. Okay, so they cannot be both constants. If both k equals 2 and d equals 2, there is an argument where you can argue that you can solve it in polynomial time. Right, so when k equals 2, you need a large number of dimensions to show hardness. On d equals 2, you need a large number of clusters to show hardness. So in the reduction, they have like n over 6 clusters or n over constant clusters. Okay, but anyway, the bottom line is the problem is hard, it's computationally hard, even when d equals 2 or k equals 2. Okay, so now we know that we have to settle for constant factor approximations. We cannot hope to find the optimal solution in polynomial time. Okay, cool. So it's hard in interesting cases. I think it's a little bit surprising. It is also, but actually there are a couple of very easy cases that we can solve. Okay, and I'm going to go through those. When k equals 1 or d equals 1, then you can solve it. Okay, and then I'm going to go through these cases, and after that I'm going to go through general methods to attack the general question and mention both what people use in practice and how we can tweak those to get provable guarantees, and well in practice too. Okay, so there are a couple of easy cases, and let me go. One easy case that actually is important for the rest of the lecture. One easy case is when k equals 1. Okay, so what is a k equals 1 case? Well, there's an input and data points, so there are points that live in d dimensions, so x1, x2, xn. And here the goal is to find the center in order to just minimize the sum of the square distances of the points to that center. Yeah? And this is an easy case, and will actually be useful for the discussion later on, because we're going to talk about the common heuristic, the so-called Lloyd's method, and this will be a useful fact to know. Okay, so again, I claim that if we have n data points in RD, and we want to find a point C, a center C to minimize the sum of the square distances, then the answer is easy. We can compute it analytically. Namely, the answer here is the center, the optimal center, is the mean of the data points, the empirical average of the data points. Okay, so basically, we just computed coordinate by coordinate, for example, right? We average all the coordinates, or we can just sum up all the points and divide by n, right? And actually, I'm not going to go through the details of the proof here. It's a calculation, but just to mention one nice way to think about it, actually, is to think about it is like a nice proof is by using that I found in Sanjay Das Gupta lecture notes, is to kind of think about the bias variance decomposition like. Okay, so it turns out, so this is very specific to the square loss here. So that wouldn't be true if we put here a different loss, like the L1, like the K-median loss, where you just put the distance here as opposed to distance squared, okay? But for the square loss, here is what we can show. We can show that given any candidate center C, right, for the square loss, then the average case means cost of my data set with respect to the center C, so this is any candidate cluster center C, right, then the average K means cost with respect to that cluster center C equals the sum of two terms. The first one is this one over here, is just the distance between, the square distance between the centers, proposed center C and the mean of the data points. Okay? And the second one is basically the average K-means cost of my data set with respect to the empirical average, with respect to mu, the empirical average. Okay, so again, given any proposed center C, basically the average K-means cost with respect to C is a sum of two terms. The first one is a square distance between that center and the average of the data points, and the second one is the average K-means cost of my data set with respect to the average mu of the data points. Okay, this is like you can prove this basically. This is something that you can go for a computation and prove it. I'm not going to go through it online. One way to try to prove it is to prove it in one dimension only, because if you prove it in one dimension only, you immediately get it in d dimensions, because this sum we can decompose the sum over all dimensions. Okay, that's just a hint how do you prove it. Okay, but why do I call this like a bias variance decomposition? Because this will be kind of the bias, right? And this will be the variance. Okay? And again, it's very, very specific to the square loss. So it wouldn't be true if I put a different alpha here instead of 2, like alpha 1. Okay, but now given this bias variance decomposition of the square loss, why is it the case that, why is this implying that basically the optimal choice here for the center is mu? Do you guys see why? I claim it immediately implies it. Why? Anybody wants to volunteer to do a quick argument? Yeah? You want to make the first term as close to 0, right? So exactly. So basically, this second term, no matter what is the choice of C, the second term stays the same. So it doesn't have the choice C in it, right? The second term appears for all possible choices of C. I will always have the exact same second term. But the first term will vary, and the smaller I can make it, the better it will be for me. And in particular, if I set C to be mu, I'll make it 0, the smallest I can hope for. Right? So as Karen says, this immediately implies that this bias variance decomposition immediately implies that the optimal choice for my center is the mean of the data points. Okay? Cool. So it's a cute proof, a cute argument of why when k equals 1, the optimal choice for the center is the mean of the data points in the square loss case. So we can compute it analytically. Okay, actually, if I have a different, just to mention, because this is actually something that, so this is known for for alpha equals 2, but if I had here a different exponent, like if I had alpha, now for alpha equals 2, the optimal choice is the mean of the points. However, if I have alpha equals 1, which is correspond to the k-median objective, then the answer is we cannot compute it analytically, number 1, and actually it's even NP hard to find the best choice for the center. Okay, so this fact is super specific to k-means. But anyway, people like k-means. Maybe that's one of the reasons for which people like k-means in machine learning. So it's anyway, k-means is much more popular in machine learning than k-median. And maybe this could be one of the reasons, because it has the nice analytical properties. So if I have a set of points and I just want to find the best center, I can solve it easily by being the empirical average of the data points for k-means. Okay, cool. So this is the case k equals 1. As I mentioned, there is another easy case, and I'm not going to go through this in class, when d equals 1, and that will be an extra credit homework for you guys. So when d equals 1, when all the points are on a line, then I claim that we can also solve it in polynomial time, and that will be extra credit homework problem. And the idea is you can do a dynamic programming then. Okay, so when d equals 1, we can also solve it. Good. How about more interesting cases? Because in machine learning, we often have points that live in very high dimensions, and we're looking typically for more clusters than just one cluster, right? So what can we say in those cases, right? You see that the problem is NP hard when d is at least 2, or when k is at least 2, right? We see that it's NP hard, but can we do something about getting maybe a good approximation to the optimal solution in polynomial time? Okay, that's the next question we're going to think about. Okay, and the answer, it turns out, that is yes. And I'm going to start, before actually talking about that a little bit, let me start with some historically, which we're going to modify a common heuristic that people have known since the 80s. Okay, so historically, actually, yeah, just to mention, actually, before going on. So, right, to go to my question, like, are there polynomial time algorithms that find a constant factor approximation to the optimal solution in polynomial time? And the answer is yes. There are several, there are several combinatorial algorithms that do so. And then if you are curious to find the best ones, you can just read my survey. I have a survey on the topic. Okay? But now today in class, I'm going to, instead of talking about the best ones that come from the theoretical computer science literature, I'm going to talk about a different algorithm that is not the best known, but it was people use mostly in practice. And this is the so-called Lloyd's method, which is what people typically refer to as k-means algorithm. Okay, but it's just a heuristic. And I'm going to talk about that one, and I'm going to discuss kind of problems if you apply it just what in a way that seems the most natural, but I'm also going to talk about tricks that people have come up with, provable guarantees, tricks that have provable guarantees and dwell in practice too. Okay, so I'm not going to go for the optimal algorithms for the k-means. I'm not going to go for the best known algorithms for k-means. I'm just going to go for what people use in practice. But still, I put a provable guarantee. I also make sure that not only tell you what people use in practice, but also what we know in terms of formal guarantees about those techniques and how we can modify them to get them with provable guarantees and Rockwell too. Okay, cool. So let's start with, so actually the most common heuristic, it's a heuristic actually, right? It started as a heuristic. The most common algorithm or heuristic for solving k-means in practice is the so-called Lloyd's method. Actually, this is what people refer to as k-means algorithm, okay? But it's really one specific approach, local search approach, to find good k-means clustering. Okay, so what is the technique? It's actually dates from 82. I checked this last night. It's only from 82. I somehow thought it was earlier, but somehow it turns out it's only from 82. Good. And so the technique is very natural. It's an EM-like algorithm, but when we have hard clusters, right? Because here we just want to have a hard assignment of points to clusters. Okay, cool. So what is the algorithm? Again, we have as input n data points that live in RD for this technique to make sense. And we're going to initialize the centers in some way, and we're going to talk about interesting ways to initialize it. So we're going to initialize the centers in some way, and then we're going to, given those centers, okay, maybe we even have some corresponding clusters. Okay, and then we're going to go through, we're going to repeat the following. Okay, as long as, so we have a current set of centers and the current set of clusters. Okay, and as long as we can improve the cost of the current clustering, we just do the following. Instead of the first, we're going to go right for rounds, and at the beginning of the round, and in each round, we're going to do two things. The first thing we're going to do is fixing the center. So we have a current candidate set of centers. So fixing the center C1, C2, Ck. We're going to find what is the optimal partition induced by those centers. So for each center Cj, I'm going to denote the cluster J to just be the set of points with the property that those points are closest to that center Cj. The most natural thing, right? So given the set of centers, C1, C2, Ck, I'm computing the optimal cluster ring given the set of centers. The Voronoi partition corresponding to this set of centers. Okay? So that's number one, and then this is what we do first. And then the second thing we do, now for each, then the second step we do, now given these clusters, fixing these clusters, C1, C2, Ck, that we got from the first step, we then find what is the optimal choice of centers. Right? So fixing clusters C1, C2, Ck, we then find the optimal choice of centers. And we know from the previous slide for the discussion on k equals 1 is that once I fix a cluster, say cluster Cj, the optimal choice of center for that cluster J is just the mean of the points that belong to that cluster. Right? Which I just argued that. Okay, so that's basically the algorithm, and it's really like EM style algorithm, right? So let me say it again. So basically, we just, right, we have initialized the centers in an arbitrary way. This is a partition. When we repeat, while we go through a number of rounds, we repeat until we cannot improve the cost of the current clustering anymore. At the beginning, so we'll have two steps, a EM step and an M step, kind of like at the beginning. So the first step is fixing the cluster centers C1, C2, Ck. I compute what is the optimal clusters that these centers induce, right? And in particular, for cluster C, the cluster say Ck would be the set of points that are closest to the center Ck out of all the centers I have here, right? So fixing this, holding center point C1, C2, Ck fixed, I pick the optimal clusters. This is the first step. And then the second step is now holding these clusters that I found in the first step, C1, C2, Ck fixed. I just pick the optimal centers. And we know how to do that because of the discussion on k equals 1. So the optimal cluster for center Cj, so the optimal cluster center for cluster Cj will just be the mean of the points in that cluster Cj. Okay, cool. So that's the k-means algorithm. And again, it's just like an EM style algorithm, but where we have hard clusters. Each point just is assigned to one of the clusters only. Okay, great. So that's k-means. This is this is the Lloyd's method. This is what people refer to as a k-means algorithm. Okay, now let's talk about properties of this algorithm. So you notice this is kind of a local search. It's really a local search, right? And each time I'm going through rounds. In each round, I'm trying to improve my current clustering, right? And how do? I do through this by using this two-step procedure here. Okay, cool. And so what can we prove about? So I'm going to go for an example in a bit, but I want to make a couple of remarks first. Okay, so I'm going to show an example. Actually, I have a few examples in a bit, but let me just make a couple of remarks first. Okay, so remark number one is that this algorithm always converges. So it will stop. Not necessarily quickly, but I argue that in general it will stop. Can somebody argue why? Well, so if you think about it, we repeat the process until there is no further change in the cost. So every time we go, I want to argue that this we're not going to repeat this while loop infinitely often, right? I want to argue that after a finite number of steps, finite in terms of n, d, and k, as a function of n, d, and k, after a finite number of steps, I'm going to stop. I'm not going to go through this repeat loop because I'm going to get to a point where I cannot further improve the cost. Okay, and let's see why. Well, first of all, obviously I go through this repeat loop only if I can decrease the cost. Right? So every time I enter this loop, I'll decrease the cost. Now, because I have n points in d dimensions and I'm looking for a k clustering of those n points, you can make an argument that at most n to the k times d. There is a finite number of partitions of those points. You can put a concrete bound n to the k times d. So if we use VC dimension style arguments, you can put a concrete bound. But even simpler, there is basically only a finite number of ways of partitioning those endpoints with Voronoi partitions, given by k centers. Right? So there are only finite number of configurations that we can take, right? And every time I enter this loop, the cost drops, right? And right, so every time I enter this loop, the cost drops, and there is only a finite number of Voronoi partitions. Okay, so that means there are only finite number of values that the cost could take, right? So that means that after a finite number of steps, this just settles, converges. Okay, so that's an argument of why this converges. Cool. All right. Now, but how fast does it converge, right? Because just converges is not too satisfactory. And so there are two questions that we care about, not only how that it converges, but how fast does it converge and what does it converge to, right? Because ideally we want to get a good k-means clustering, right? Not only just the output of some local search algorithm, right? We want to be able to understand, do you get good quality solution or not, and how fast do we get it? Yes? So the shape is like as I had here, actually. So just to be oh, I see. It's kind of a Voronoi partition. So the space looks like a Voronoi partition. But yeah, they tend to be round. Okay, so K-means kind of encourages round clusters. But like formally, the shape, once I have K centers, if I'm to partition the space according to which point, which center are closest to, looks like a Voronoi partition. But you are right. Kind of, this is an informal statement. Basically, like it's observed, and you can, right? Informally, you can argue that the center, right, the shape of the clusters produced are kind of round. Okay, good. Now, right, so let's think about, right, so it always converges. Okay, so these are good questions, so definitely ask questions, okay, to make sure that we're on the same page. Okay, so it always converges, but how fast and what solution does it converge to? Okay, and it turns out that the answer is interesting, actually, okay, and the point is that the initialization is crucial. Okay, so actually the initialization is crucial both for both of the questions that I was asking. The initialization is crucial both for understanding how fast it converges and for understanding the quality of the solution output. Okay, and I'll actually, so in the next part of the lecture, I will discuss some techniques for initializing, and I'm actually going to talk about techniques that are commonly used in practice. And I'm going to talk about some classic ones, like from the 80s and so on, like the pick random centers from the data points. That's the classic one. Maybe repeat that a few times. It's a classic one. So I'm going to talk about, and another classic one is the farthest traversal. I'll make that concrete. So these are classic ones, but they do not come up with provable guarantees. Okay, even if people use them widely in practice. And then I'm going to talk about a cool one, a cool recent one from about 2006. But not only is widely used in practice these days, it appears in all packages like R, MATLAB, and so on, but also has provable guarantees. So it's definitely something that I would try if I had a K-means clustering problem. Right. Yeah, and as I mentioned, actually, I'm kind of really surprised because this is such a popular technique used in practice, K-means, and also the Lloyd heuristic. I'm quite surprised that, like, even the hardness is all for K equals to or equals to or only proven in 2008. It's a little bit surprising that kind of the K-means plus only appeared in 2006, right? Because given that they are so widely used, you'd expect that people would try to really understand and to make them even better, right? So in any case, luckily these days we know techniques with both provable guarantees and that work well in practice. So I think that's important. Okay, cool. So, right. So let me start with the simplest one, so the random initialization. And actually, that will also give me the opportunity to go through a couple of examples, right, to show how the K-means algorithm works. Because I think some of you guys like examples. Okay, so let's go through an example of. Okay, so I'm gonna write. Actually, so I'm making this. I'll do the same thing that most people do. So, like when I mean the K-means algorithm, I'm talking about the K-means algorithm. I really mean this Lloyd's method. This local search heuristic, yeah? So it's either, I'll call it either Lloyd's method or the K-means algorithm. Okay, so let's go for a couple of examples, right? So let's think about this Lloyd's method, this local search procedure, what everyone calls the K-means algorithm. And let's think about the random, let's pick the centers at random, right? So assume that I have this data set, and let's assume that I'm looking for 3 clusters, and let me just pick the centers at random. So maybe I pick these 3 centers. The green one, the red one, and the black one. Okay? Good. So what will happen then? So if I pick these centers, right, what will happen? So, right, so I'm going to go through the Lloyd's method. Okay, so these are my 3 centers that I picked. Okay, good. And then what do? We'll first assign each point to its nearest center, right? We first compute, so given these centers, we first compute the optimal clusters. And in this example, this is how the optimal clusters will look like, right? Then we are going to compute, so these are the optimal clusters, current optimal clusters. Then we're going to, what do we do next? What do we do next? Yeah, we recompute given these clusters, we then recompute the optimal centers for these clusters, right? And what will be the optimal centers for these clusters? I just take the average of the data points in those clusters, right? And this is how the new centers are going to look like, right? Okay, cool. Now, what do we do next? So now these are the new centers. Now we're going to go through the next iteration of k-means, right? So these are my current centers. My fixed centers are the red, the green, and the black one. And then what do we do next? We're going to compute the clusters, the optimal clusters, given these centers, right? So we're going to now assign each point to its nearest center. So for example, this point over here, we're going to move to this guy, because this point over here will be closer to the green center than to the red center, to the current red center, right? And similarly, this point, we're going to move to the red one, because now this point now is closer to the red one compared to the black one, to the black center, right? So I'm just going to assign now each point to its nearest center. And this is how the assignment looks like, right? Now this guy switched the assignment, this guy switches the assignment, and now the new cluster is going to look like this, right? These are the new optimal clusters. And how do I do next? Yeah? I recompute the centers, exactly. So what is, I'll get for each of these clusters, I get the mean of the points in that cluster, right? And this is how my clustering looks like currently. And then I'm going to do the same, right? And then I'm going to repeat. Then I'm going to, for each of the points, I'm going to see, for each of the points, I'm going to, oops, sorry, I went too fast, right? For each of the points, I'm going to assign them to their nearest center, right? Right? So for example, this guy will switch from being assigned to this center to being assigned to this center, right? And then I'm just going to recompute the clusters, right? And again, for each of the clusters, I'm going to recompute the optimal centers, right? And then I think at this point, then the process will settle down, because we have 3 clusters, and each of the centers is the mean of the points in that cluster, and each point is assigned to its nearest center, right? And then this is when the Lloyd's method stops. Okay, so that's an example of running k-means. It's fun to think about it. Okay, cool. Now, so right, so it does converge as we argued, and in this case, actually, it did converge to the optimal solution. Okay, we're lucky. But in general, it can converge to arbitrarily bad solutions of arbitrarily bad quality. Okay, and so and here's a simple example where it converges to a local optimum, but is different from the global optimum, and effectively can make it arbitrarily worse compared to the global optimum. Okay, so this obviously shows that you don't want to run Lloyd's method blindly by picking centers arbitrarily, because you might be doing really badly. Okay, and I think the same thing is actually also true for EM. So the EM algorithm is less analyzed from a formal point of view, but I bet because this is a limiting case of EM, right? It's really a limiting case of EM. So I'm sure that one can show that the EM algorithm can also converge to really bad local optima. Okay, so it's kind of really important to think about the quality of the optimum that we reach. Okay, here's a simple example where the Lloyd's method gets to something really bad. Okay, so let's assume that we have 9 points like this one, this point here. And we're looking for 3 clusters, okay? And let's assume that my centers, the centers that I pick initially are these red, green, and black center. Now I claim that I'm locked in place, right? I claim that these centers induce this clustering, right? And moreover, it's a stable solution. It's a local optimum. Why? Because basically each point is assigned to its nearest center, if you think about it. And each of these centers is a mean, the average of the points in that cluster. So that's a local optimum. So this is basically, I claim that this clustering over here, it's a local optimum. So Lloyd's method will just stop there. Okay? But it can be arbitrarily worse compared to the global optimum. Because if you think about it in this example, so this is the local optimum that we've been talking about with these horizontal clusters like this, right? But the global optimum is in fact this clustering over here, where I put with this green center here, the second center, the red one here, and the first center here, the black center over here. So this is the optimal solution, right? And if I make, say, just for simplicity, I'm going to make these distances here. I can make this to be 1, right? And I can obviously make this arbitrarily large, right? I can make this length, the distance between this point and this point, arbitrarily large. And so then I can make the quality of the cost. So the ratio of the cost of this clustering to this clustering, I can make it arbitrarily large. Right? So this is the optimal solution. This is what Lloyd's method might output. It can be arbitrarily bad, not good. Okay, so it's a simple example where the Lloyd's method does really badly. So the natural k-means heuristic with just a non-thoughtful choice of centers could do really bad. And again, this is probably a problem for all local search algorithms. Okay, cool. Now, but okay, the next question that I would expect from you guys is, sure, you show me an example, but maybe it's a contrived example, right? Maybe in this example, maybe this is not a general example, maybe it doesn't appear in the real world. Maybe you're going to tell me, maybe for all real world data sets, we're not going to have this nasty structure, and so maybe Lloyd's method will do great then. Okay? You might wonder, right? But turns out that the answer is interesting. So if we use random centers, okay, let me focus right now on using random centers. So if I use random centers as a way to initialize the Lloyd's method, actually the Lloyd's method could do bad, could output a solution that is locally optimal and far from the global optimum, even when the data is really nice. So imagine that we have data that is given by a mixture of Gaussians that are very far apart. So I have 3 Gaussian components that are very far apart, super well separated, nicely separated. I claim that if we use Lloyd's methods and use random initial centers, there is a good chance, we're going to get, there is actually quite a good chance, a very high chance, we're going to get to a bad solution. Right? So basically, if we use a Lloyd's method, this K-means heuristic, and use random initial centers, this could do bad even if the data is given by Gaussian clusters that are very well separated. Okay, so why? Because I have here a small example with 3 clusters. Right, so I have 3 well-separated Gaussians, right? And why is it random initialization not good here? Well, because what could happen? So if I pick exactly what I did here, if I pick 3 random centers, there is a good chance, a constant chance, that 2 of the centers are going to fall in the same cluster. Right? So let's assume that they all have about the same probability mass, right? These Gaussians, and if I pick the centers at random, there is a good chance I get this picture over here. I have the green center and the black center in the same cluster, and then I have the red center over here. Okay, and this is my starting point. What do you guys think will happen with the Lloyd's method? What will be the cluster's output at the end of the Lloyd's method? Perfect, right? Your name is? Leia. So as Leia is saying, like if this is the starting point for the Lloyd's method, basically we end up splitting these clusters into 2, this cluster over here into 2, and then all these points here will be clustered around the red center, right? So the red center will move after we go through the iterations of the Lloyd's method, but at the end of the day, we're going to get this picture. Okay, so we'll end up splitting a true target cluster, a true optimal cluster into 2 parts, and we'll end up merging 2 clusters. Okay? And there's a constant probability that this will happen. And actually, if you think about it, if the number of clusters is large, like if K becomes larger, you can go actually through a computation that I'm not going to go through here. But the point is that when you make K larger, the probability becomes larger and larger. The probability that you'll actually get this picture where you have two centers in the same true cluster becomes larger and larger. So it becomes more and more likely as the number of clusters increases that I'm going to get this picture where I pick 2 centers on the same true optimal cluster, which then leads to, when I run the Lloyd's method, to splitting the cluster into 2 and getting a suboptimal solution. Right? So as K becomes larger, you can go for a computation and argue that this becomes more and more likely that something, that the Lloyd's method will output, very likely that the Lloyd's method will output something bad. Okay, so random centers is no good. Just even for very, very natural data. So using random centers is not good. Okay? But for the Gaussian case, there is a very easy fix. Right? If you go back here, like for this Gaussian case, like if the data is truly Gaussian, well-separated Gaussians, if I give it 2 minutes, you're going to come up with a fix. You're going to come up with a way to pick the centers well. Okay, do you guys have any ideas? Okay, yeah? Well, I don't want to do first, like I don't know the Gaussians. Sure, if I knew that the Gaussians, I could first somehow learn the Gaussians, then I would pick the means of the Gaussians, right? But that's the whole point. I don't want to first learn them. Just want to run clustering on it to kind of find the points that belong to each Gaussian. Okay, let me mention a heuristic that people tried. Actually, it has also been very popular. So what turns out to fix the Gaussian case is to do the farthest point heuristic. Okay, what you do, you first pick a first center arbitrarily, maybe at random. And then the way you select the next centers, the next set of centers, at each moment in time you have a number of centers, C1, C2, Cj minus 1. And the way you select the next center to add, you just pick a point that is farthest away in your data set from the current set of centers. Right? Very natural. So I pick the first center arbitrarily, and then at each moment in time I have a number of centers around C1, C2, Cj minus 1. At which point should I add the one that is farthest away from the current set of centers? supernatural. Okay, and it does fix out the Gaussian case. So, for example, here maybe I pick this as the first center, right? Then I pick the point that is farthest away from this center, so then there will be this green point over here, right? And then I'm going to pick a point that is farthest away from both the red center and the green center. And then this will be this black point over here, right? And if I do so, I'm guaranteed that the centers that I pick, they'll all be from, in the Gaussian case, they're all going to be from different clusters. Okay? And then if I run the Lloyd's method, well, the clusters are well separated, then I'm going to get the right clustering that I'm looking for here. So things will be great. Yeah? Cool. All right? So that's the, cool, that's the, so the farthest point heuristic does fix the Gaussian case. Okay, but it has a problem. So, I mean, things are not as simple. And it is a common heuristic, and people use it a lot. I mean, it's a very natural fix for the Gaussian, but it has the problem, and people notice it in practice. Okay, and then you can also formalize it. Turns out that it actually can be thrown away by outliers. So it is very sensitive to outliers. Okay, and here's a simple example. Okay, and then we're going to go through this example, and then it will motivate so it's the random initialization, then there is the farthest point, the heuristic initialization. We're going to see a problem with this, and then this will motivate a way to the initialization that has provable guarantees and does work well in practice too. Okay, so here's the problem with the farthest point heuristic, right? As I mentioned, the problem is it is super sensitive to outliers. Okay, so let's imagine that we have this data set like this one here, where we have most of the points lie in these three clusters, right? So imagine that we have a lot of points here at -2, 0, a lot of points here at 2, 0, 1, and a lot of points at 0, -1, right? And good. And so let's assume that we have just one point sitting at 3, 0 over here. Okay, cool. Then what will happen here? So now this point is far away, like, so you see this is kind of an outlier, right? This point is far away, but it's not so far away that it should be in its own cluster, right? So actually the optimal solution would be to have a cluster here, a cluster here, and maybe attach this point 3.0 to this cluster over here, right? Because again, the vast majority of the points, I'm going to have many, many points sitting here, and many, many points sitting here, and many, many points sitting here. Okay, and so, right, the optimal solution would really be to have this cluster here, maybe we'll attach this point to this cluster over here. One case free. Okay, but what would the farthest point heuristic do? If I pick first this to be my first center, right? What would be the next center? It will be the point over here. Cool. Okay, it will be the 3, 0 because this is the farthest away, right? And then what is the next center? Either one here or one here. So say it will be a point here, right? And then what happens if when I run the Lloyd's method from that moment on? If I run the K-means heuristic from that moment on, what does it happen? What will be the clustering output? Exactly. And your name is? Ronald. Okay, as Ronald says, I see you every single Sunday. So right, as Ronald says, basically it's exactly what happens. So these two clusters will be merged, right? I will have a cluster here. This will be a cluster here. These two clusters will be merged, and this point will be in its own cluster, right? And this the K-means, so this is a local optimal solution, right? And it could be arbitrarily bad compared to the globally optimal solution. Right, because as I mentioned, the globally optimal solution would be to have here a cluster here, and then to attach this point to this cluster that will have very, very small cost. Because especially if I superimpose these points, it could be close to 0 the cost, while the cost of this one can be large, right? So it can be an infinity ratio a very, very large ratio between the quality of the solution output if we use the farthest point heuristic initialization versus the cost of the globally optimal solution. Okay, so that's not good either. So random initialization doesn't work always. It actually doesn't even work if we have nice clusters, well-separated clusters. Farthest point heuristic also that is thrown away by outliers. Can we do something in between? Okay, and the answer is yes, luckily. And the idea is to do this technique called the K-means ++ heuristic, where basically we just interpolate between these two techniques, between the random initialization and between the farthest point heuristic initialization. Okay, and how do we do it? So let me mention it. It's a very cool thing to know. Okay, super useful in practice and with nice properties. Okay, so what do we do? Basically, given a set of centers that we've had so far, I'm going to go by d of x, the distance from a point x to the current set of centers. So the minimum distance between the point x and one of the centers. Okay, and then all I'm going to do, I'm going to sample the next center in a way that is proportional to d squared of x. Okay, so let me say it slowly. So I'm going to first pick C1 at random, the first center at random. Okay, and then I'm going to add k minus 1 more centers. So for j from 2 to k, I'm going to pick the center Cj among the data points. And how I'm going to do it, I'm going to pick it in a probabilistic manner. So for each of these data points, x1, x2, xt, I'm going to have a probability that is proportional to the square distance between my point and the current set of centers. Right? So given h point, xi, I'm going to have a smallest distance from xi to the current set of centers. And I'm going to pick the next point to add in a way that is proportional to the square distance between my point xi and the current set of centers. Okay, so that's called k-means plus plus. So is this clear, the definition of the description of the algorithm? Right, so basically, and it's crucial here to use the distance squared of x. So this is kind of the contribution, right? If this is my current set of centers, C1, C2, Cj minus 1 is my current set of centers, when this squared of x for a point x is this is the current cost that that point incurs for the current set of centers. And what I'm going to do, I'm going to pick the next point, if it is proportional to its contribution to the current cost. Right? So if a point is very, very far away, I will have a good chance I'm going to pick it. But I'm not going to do it in a deterministic manner. I'm going to do it in a probabilistic manner that will smooth out kind of the outliers effect. Okay, and let's see what happens. So this is basically what k-means plus plus does. And actually, it turns out that it does have good guarantees. I'm going to run it in actually, let me come to the guarantees. Oh, no. Okay, actually, let me go here and show the example. And I'll come back to the guarantees. Okay, so let's see what happens if k-means plus plus this example. So in this example, let's assume that the very first point we pick is this random red point here. Yeah? Now, sure, this point is farthest away. So this point over here is farthest away from this red center. But it's just one point. And it's not so much far away compared to these points that sit in these two clusters over here. And because it's just one point, sure, its probability of being picked will be larger than the probability of any of these points. But because I have so many points here, right, and I'm picking according to the induced probability distribution, there will be a good chance that the next point that I pick is actually a point that comes from this cluster. Right? And similarly for the next one. Okay, so basically the Lloyd's method fixes the problem here. Okay, and it turns out that it's a good technique. It fixes the problem, outlier problem here, and it turns out that you can show that it's a good technique in general. So in general, you can argue that no matter what is my set of points, if I initialize according to the Lloyd's method, then the clustering that I get after the initialization is a log k approximation to the optimal k-mean solution in expectation. So that's very good, right? Because we've seen that the other techniques of initializing did really badly, could be arbitrarily worse. But this k-means plus plus technique works no matter what is the set of data points. So no matter what my data points look like, if I initialize using the k-means plus plus technique, I'm guaranteed to get a clustering at the end of the initialization step whose cost is only within a log k factor of the cost of the optimal solution. So that's nice. I think it's really nice. Okay, and so then basically, so that's even in the initialization step, we get a log k approximation. And then if we further run the Lloyd's method from that moment on, we can only improve the cost. So we can, if we want, we can also run a few steps of the Lloyd's method. I mean, why not? But we can stop at any time and do a guarantee that we are not doing too much worse compared to the optimal solution. Cool, right. And actually, I already mentioned that this k-means plus plus appears in all the standard packages. So I think it's one of the methods that people use for doing k-means these days. Okay, so any questions about this? K-means plus plus, yes?
So what if we choose the outlier? Do we run multiple times of k-means plus plus to get the one clustering that minimizes the
Right, so this is an expectation. So that's a good point. So the guarantee is an expectation. So to get with high probability, you might want to run it a few times. Okay, so right, the guarantee is an expectation. So there is a chance that I'm also going to pick, I'm going to doing something wrong. I'm going to pick the outlier, right? But if I know that if I run it a few times, with high probability, I'm going to do something good. And your name is? Okay, cool. Sounds very interesting. Well, it's hard for me, that's all. Okay, cool. So that's k-means plus plus, but I'll definitely remember it, which is what matters. Okay, cool. So, right, this is k-means plus plus, right, and it was proven actually the favor with this initialization does well. It was proven actually in 2007. It was a soda paper by David Arthur and Sergei Vasilevsky. Okay, and Sergei has been at Yahoo and then at Google. You know, he's running the algorithms group at Google. So, I mean, I'm sure that all these companies actually use k-means plus plus heavily. Okay, so good, great. Cool. And as I mentioned, we can then run Lloyd's method to further improve the cost. Okay, just a couple of comments. So, right, so just to mention, so as I mentioned, for the k-means plus plus, given a current set of centers, we pick the next center whenever it is proportional to the, right, you know, it is basically proportional to the current cost, to the current cost of my point to the k-means cost of the clustering given by the current set of centers, right? So I need to pick here, the next point will be proportional to d squared of x, where d of x is the distance from my current point to its closest center, current center, right? So but it's crucial to pick d squared of x to get the provable guarantees, and that's natural because it corresponds to the cost in the current solution, right? And just a couple of comments. So when we pick k-means, for k-means plus plus corresponds to alpha equals 2, right? Actually, if you pick alpha equals 0, this really corresponds to random sampling, right? Because if alpha equals 0, that means I pick all points in the same, the same weight, the same probability, right? And when alpha equals infinity, that means I'm going to do the farthest traversal heuristic. So the point that has the largest distance will have the highest, basically we're going to pick that deterministically, right? So if you think about it this way, this is a formal way in which in this k-means plus plus heuristic we interpolate between this random sampling and between farthest point heuristic. We pick alpha 2, we don't pick alpha 0 or alpha infinity. It's a smooth way between the two extremes. Okay, and it does well in general, probably. Okay, and actually just a comment on if we cared about k-median, where the goal is to minimize the sum of the square, just to minimize the sum of the cost of the point around a cluster center. But so then it will correspond to alpha equals 1, and if we want to initialize k-median, we want to pick alpha equals 1 in the initialization, and then we also get provable guarantees. So we have to use the cost when we initialize the actual objective function when we do the initialization. Okay, and I'm not gonna, right, and so as I argued, so this algorithm does well in general. We get a local approximation. It fixes the problem in our outlier example. Okay, and, right, and good. So that's nice. Now, how about the running time? Okay, so I claim that, okay, so let's think about the running time both from the k-means plus plus initialization point of view and from the point of view of the Lloyd's method. What is the running time, right? If we have endpoints in d dimensions and we are thinking about k clusters. Okay, now I claim that actually the k-means initialization takes, so if we are just tiny bit smart, we can initialize it so that when we add each center, all we have to do is to do one pass for the data and or computation that is n times d, because basically, right? Because we have endpoints. Any of the endpoints is a candidate center in d dimensions. I have to compute kind of, and for each point, maybe I stored the smallest distance to the current set of centers, right? So then I have to do n times d computation to add a new center, and I have to do it k times. So in total, the running time will be n times k times d. Okay? And this is k-means plus plus. I just want to mention, I'm not going to go through the details in class. Actually, there's some algorithm called k-means parallel that speeds this up, if you're interested in something even faster. Okay, now how about the Lloyd's method, the Lloyd's technique? What is the running time of each of the iterations of the Lloyd's method? So what is the running time within this repeat loop? Yeah, so it's written on my slide. So the running time will be basically So it's again n times k times d, because really this is the unexpensive step is this one over here, the second step. The expensive step is the most expensive step is the first step, where given the new set of centers, we recompute the optimal partition, and in the worst case, the new set of centers change completely. So we have to basically, for each point in the data set, we have to compute the distance to all centers, and so then it will be an n times k times d computation. Okay, so the running time of the inner loop of the Lloyd's method is n times k times d. Okay, so that's the running time with the inner loop computation. Now, how many rounds do we need to converge? Okay, so right, I showed an example at the beginning of the lecture where I showed that it can converge to really bad states, right? But does it converge fast? You might also ask this question. Does it converge quickly? That's important too, right? So the step, so each of these iterations, right, through the Lloyd's method takes only time n times k times d. Okay, so that's good, not too bad. But how many of these iterations do we need? Okay, now in practice, it turns out that in some data sets converges very quickly, 100 iterations, even smaller. Now, but how about the worst case? Well, it turns out, again proven in the SODA 2007 paper, in the worst case, it can take exponential number of rounds to converge. And this is again in 2 dimensions. It's really surprising. So like Sergey Vasilevsky and David Arthur showed an example where they somehow encoded a binary counter, and they showed an example where this Lloyd's method can take exponential number of steps to settle down, to converge. Okay, but in practice, does converge much faster, and so, and actually, not only that, but it turns out that actually, if you think about a so-called smooth analysis model, so if you don't think about a worst-case data set, but you think about a smooth analysis model, where you first get your data points and you perturb them a little bit, and then run the Lloyd's method, then you can argue that it converges in expected polynomial time. Okay, so there is a, right, so okay, so what is smooth analysis? This is your original data points, right? These are your original data points, you perturb them slightly. Okay, and then we run Lloyd's method. When there are formal results, very recent formal results, that show that if you do so, the Lloyd's method will gonna converge quickly in expected polynomial time. So that's kind of cool to know, because it's just another way to run, say, the Lloyd's method in practice, you know, or to run k-means plus plus. Yes.
Is there a specific configuration that would make putting it into the worst case, or do you have a picture?
I do not have it here. It's very convoluted. It comes through a reduction. It encodes a binary counter. Yeah, so it's the reference. If you are curious, you can find it. You can find it in this paper. So it's a non-natural instance. Yeah, because actually, what this smooth analysis analysis shows, right, of the Lloyd's method shows. Well, if I take my points and I slightly perturb them according to small Gaussian perturbations, and then I run the Lloyd's method, then it will be fast. Okay, so it kind of all this smooth analysis result kind of implies that lower bound that shows that Lloyd's method can take exponential number of steps in the worst case. It's kind of unnatural, right? Because anything that comes from real world data, or we have a little bit of noise anyway in the data, Lloyd's method will gonna converge fast. Okay, cool. And so I'll try to see if I have time to go through my next topic, which will be hierarchical clustering. But okay, cool. But let me summarize the k-means and k-means plus plus. Okay, so basically what we've been talking about is, so I think first of all, the k-means is one of the most widely used techniques to cluster data in machine learning, and not only, throughout science and computer science. So it's good to understand good algorithms, and we've been talking, it's NP hard in the worst case, the problem, but there are there is this very popular technique called the Lloyd's method, or the k-means heuristic. It can lead to really bad quality solutions. It can take exponential number of steps to converge, but its properties depend on the initialization in terms of the quality of the solution, and there is a nice, elegant, simple way to do initialization, the so-called k-means plus plus algorithm that comes up with provable guarantees and does really well in practice. Okay, it's something that I would use. Okay, and yeah, cool. So that's a summary of k-means plus plus. Any questions here?
K-mean also applied to kernel methods.
It's excellent point. So you are Kelly, right? Yes. So Kelly, no, she makes an excellent point. I didn't put it on my slides. I meant to put it on my slides. So if you think about it, because k-means is like we care about the square distance, right? All we need to do to run k-means is to compute the square distance between a point and the center, for example, right? Well, you can kernelize that because if you expand out the square distance between x minus y, square distance of x minus y squared, it will be x dot x minus 2 times x dot y plus norm of y squared. This will be, so it will be x dot x minus 2x dot product y plus y dot y, right? And then it's only operates via dot product computation, so that means I can kernelize it. Excellent point. And actually people have kernelized it. And then if they kernelize it, then it leads to shapes that are not convex potentially in the original space, which is nice, right? Because when I mentioned the decision, kind of the type of shapes that k-means are the Voronoi partitions induced by k-means are convex in the original space. But if I kernelize it, it might be non-convex in the original space, so we can get benefits. So it's very nice. That's why it's so useful. Like, that's why people probably like it, because you can kernelize it. It does well in practice. We have good way to initialize it, and so on. So excellent point. Okay, and I only have 10 more minutes. Okay, so I wanted to also talk about actually hierarchical clustering. So let me try to see if I can do it. It will be very rushed. But okay, if necessary, I can start there next time. Okay, it's another very important topic. Okay, cool. But and actually, it's motivated also by these questions, so key questions. So far, I just assume, oh, let me assume that I know K. Okay, but how do I know K? Right? I have a data. I want to cluster customers by their behavior, for example, right? Or I want to cluster in Facebook. I want to cluster users by their interest. How do I know K? What K should I pick? Right? It's actually that's basically the kind of the main problem when you do objective-based clustering. It's actually the kind of the main issue, but maybe it's not yet, answered yet. Okay, but there are some answers. What people do normally in practice, let me mention some. What people normally do in practice, they just try to find the value of K. You run k-means for various values of K, and you're going to try to find the value of K for which there is a huge gap between between the k minus 1 means cost and the k means cost. Right? If you increase a little bit K and suddenly obtain that the quality of the solution is much better, that kind of means that maybe the k minus 1 was not a good choice for the number of clusters, and maybe K is the right number of clusters. Okay, this is a very common used technique. Okay, and actually, while at this point, I also want to mention that, as I mentioned, k means plus plus actually gets a log K approximation in the worst case. But if my data is nice, so that there is a huge gap between k minus 1 cost and k cost, actually k means plus plus can be shown to do much better. We're going to give a constant factor approximation. So the data has even nicer structure. K means plus plus behaves even better. And there has been work showing that. Okay, so it's another nice property. Okay? But going back to the value of K, right? So how should we choose K? Well, as I mentioned, one way to do it is to use this heuristic. Another way would be to try to learn somehow K from data from related problems. Maybe you can do some sort of supervised learning to learn K. Another very different way is to just even abandon the idea of outputting a partition and try to output a hierarchical clustering where you capture kind of structuring data at various levels of granularity. Okay. Now it turns out that actually some very simple examples, if you try to, you might wonder can I put in a hierarchy, like if I have a data set and I'm looking about optimal K, optimal 1 means clustering, optimal 2 means clustering, optimal 3 means clustering, can I put all of them in a hierarchy? Are they laminar? Turns out that the answer is no. Okay. So when we do a hierarchical clustering, people think about different techniques. Okay, and that will be my next topic. Okay, and this one also has additional motivations beyond what I mentioned. I think I actually have maybe like 10 minutes, so I'm going to try to go through it, okay? Cool. So what is hierarchical clustering? So basically, like in this example, in many cases, a hierarchy might be more natural as an output of a clustering algorithm compared to a partition of the data. Right? So for example, in this example over here, why? Because, depending, first of all, different users might be interested, like if you're trying to cluster, say, news, or you're trying to cluster documents by topic, right? And different users might be interested in different levels of granularity. Maybe some users not be interested at the level sports fashion, wouldn't care about details about soccer or tennis, right? And moreover, even at the same, even we have the same number of clusters, maybe different users will be interested in kind of different types of clusterings, right? Somebody is more into sports, or somebody more into fashion might prefer this kind of this clustering over here to this clustering over here, right? So somehow having a hierarchical clustering might be better. Okay, it's be more suitable. Okay, so that's why people have spent a lot of time devising clustering, hierarchical clustering algorithms in machine learning and not only. And there are at a high level 2 ways to do hierarchical clustering. The first one is top down, where we start with all the points in one cluster, and then we split the whole set of points somehow into 2 parts. Maybe run the 2 means algorithm, we get 2 clusters. Maybe I get this cluster over here and this big cluster over here. Okay, and then inside of them I recurse. Okay, and then if I do so, I get a hierarchy. So it will be a top-down construction of the tree. Okay, now another way to construct the tree is to go bottom up. Okay, so here what we're going to do, we're going to start with each point in its own cluster, and then we'll repeatedly merge the 2 clusters that somehow are closest to each other. Okay, and now there are various algorithms that define the notion of closeness in different ways. Okay, so that's when we talk about bottom-up clustering, this is the main question. So how do I define the closeness between 2 clusters? Okay, and there are a few common ones, very so-called single linkage, very so-called complete linkage, and a couple of others. Okay, so here basically the question is: so if we start with a measure of similarity between pairs of points, we sort of assume that a measure of distance, right? So we said at the beginning that the input to a clustering algorithm is a set of points and the distance function between any 2 points, right? So if we start with such a measure of such a distance function, then the question is how to define the distance between sets of points, right? This will be my current cluster that I have around at the moment in time. Okay, and different algorithms define them in different ways. So for example, the single linkage algorithm defines the distance between 2 clusters A and B as being the minimum distance over points X in A and Y in B. Okay, so here's a single linkage basically, right? So what we do, we start with each point in its own cluster, like maybe we start with all points in our own cluster, right? And then the distance between any 2 clusters now is just define the minimum distance over a point X in the first cluster and Y in a different cluster, the other cluster. Okay, so we start with points in our own cluster, and then at this moment in time we just merge the 2 closest clusters. Okay, so in this example here, like if these are my points on the real line, so this is -3, -2 location, this is A at -3, B at -2, C at 0, and so on, right? When the 2 closest points will be these points, A and B, then D and D I'll merge next because they are the closest. Now, the distance between C and AB will be 2, and smallest among all the remaining distances because the distance between C and D is 2.1, and the distance between the blob D, E, and F will be much larger. It's like 2.8, right? So now the next merge that I'm going to do, I'm going to merge point C with the cluster AB. Okay, now I have the blobs that I have around are ABC, DE, and F, right? And now the distance between the blob ABC and DE will be the minimum distance between points in these 2 clusters. So it'll be basically the distance between D and C, so it's 2.1. And that's smaller than the distance between D, E, and F. Right, and so I'm going to do this merge. And then the last one. Okay, so this is how the run of the single linkage algorithm is going to look on this example. This is called the dendrogram. It's nicely used in many fields like social sciences and so on, computational biology and so on, because it gives a good visualization of how data clusters at various levels of granularity. Okay, this is single linkage. How about complete linkage? So complete linkage, as I mentioned, oh, I see. And there is another way to run this algorithm. You can also represent the same thing in a different way if you want. Okay, and it's connected to the so-called classical algorithm for minimum spanning tree. Okay, but let me go to complete linkage. So in the complete linkage, basically the main difference is that now the distance between 2 blobs is defined as a maximum distance between points in one blob and another blob. Okay, and now one way to think about the complete linkage, I'll be done in a minute. So one way to think about what the complete linkage does is it's basically at each moment in time is trying to keep the diameter as small as possible, right? Because now the distance between 2 blobs is a maximum distance between a point in the first blob and the point in the second blob, and I'm going to pick to merge the 2 blobs that have the smallest distance. And this is, if you think about it, what this means is that at each moment in time when I'm doing the merge, I'm trying to keep the diameter as small as possible. Okay, so for instance, in the same example that I had for single linkage, what I'm going to do the first 3 merges in the same way. I'm going to first merge A and B, then D and D, then I'm going to merge A, B, C, A, B with C. But then instead of merging A, B, C, and D, E, because if I do so, the diameter will be 6.2. The next merge that I'm going to do, I'm going to merge D, E, and F, because the diameter will be smaller. So then that's my next merge, and then that will be the final merge, right? So this way is different from single linkage. I'm trying to keep the diameter as small as possible. Okay, now both of these algorithms actually, and that's another way to view the same sequence of merges. Actually, I want to mention that both of these algorithms are kind of not robust to outliers, and this has been observed in practice, including in my own experience. But there is some method that is called the words method. It is more robust to outliers, and actually it very nicely connects to k-means. So what we do in the words method, so we have a number of clusters around, and at each moment in time, we're going to try to merge the two clusters, so that if we then do the merge, we have the minimum increase in the k-means cost. Okay, so that's basically, and then you can put down a formula that exactly captures this intuition. Okay, and then you can run it through this example, right? So basically what we do in the words method, we are trying to merge the two clusters, so that if after we do the merge, we get the minimum increase in the k-means cost. Okay, this turns out, there are no provable guarantees for it, but it turns out to do much better in practice than the single linkage and then complete linkage. I'm going to skip the running time, just show some plots. So actually, you can, some experiments that we have done, actually, you can show that the words method is much more robust to outliers. Okay, cool. But just to summarize, I'm going to skip this topic. Just to summarize, we've been talking about clustering. It's a very useful technique for basically it's learning from unlabeled data. And we've been talking about both algorithms that output a partition of the data and hierarchical clustering. Okay, and these are things that you guys should know. Questions? Yeah, actually just to mention, there is one topic that I didn't cover, but it's a very modern topic, so it's so-called overlapping clusters, actually. So like the most modern viewpoint on clustering is that sometimes you might not necessarily want to output a partition, but what you might want to output is overlapping clusters. It is motivated by the fact that in social networks, if you think about communities in social networks, a person might belong to the community of friends, to the community of, to his family, to the community of scientists. So in many, many natural cases, a person might belong to multiple communities, and they might not form a hierarchy. And so then a very hot topic in clustering research these days is to output overlapping clusters. And there is a lot of debate what is an overlapping cluster and so on. Cool.